Surface tension. So in liquids, the concept of surface tension is actually not that easy to be able to understand. And I'll try my best to be able to help you. I'll also put some kind of references in the description as well, okay, that have helped me in order to think about this. And definitely, okay, a chat with ChatGPT has helped a little bit. It didn't help as much as I wanted, but okay, so OpenAI, thank you. Okay, so what is this surface tension? And let's try to get intuition into this if you've never kind of run into this before. So before I proceed, what I would want you to think about kind of just from the beginning is to take yourself back. And if you think of solids, so let's say if you have a solid table, and this particular solid table that you have, you're going to place something on this solid table. So let's imagine, that we're going to be placing a ball in here, that we put it on top. Now we're very familiar with the idea and concept that if you place this ball, then you have the weight of the ball, which is trying to pull it down. And technically, what this ball would try to be doing is it would try to break through the actual table, right? So it would try to break. Now, if it does not break through the table, right, and it's just held up at an equilibrium point, so it's just basically just static, not moving, then of course you will agree that in order for that to happen, so from Newton's laws, if we would draw the full body diagram, we would have an equal force, which would be in the opposite direction. And we would call this the force of normal. And these two, so the weight and the force of normal, would be equal to each other. And this particular ball is not going to be accelerating or moving through the table itself. Now, if you zoomed in on the table is made up of various particles. So, from atoms and molecules, whatever the composition is. And as you put this ball on top of the table, then what that ball is going to try to do is going to try to displace all the molecules and particles that are being held together. However, those molecules, I'll just refer to them as particles. So those particles that you have, they have extremely strong bonds in between. And those particular bonds do not allow this ball to break them. And because it doesn't allow them to break them, or at least it doesn't have enough force to break them, right? So they're strong enough to withhold. So what's going to happen is if the ball is pushing down on these, they're going to be pushing back against, right? So they're going to try to hold themselves in. So it's almost like in cohesion, okay? As one unit, they're trying to stay together. Now, this word cohesion is going to be important for us to understand these surface tensions that exist. So that's the first thing that I would want you to bring back and think about. Okay, we have these particles, even in solids, they're there, and they're trying to hold themselves in so no object actually falls through. Now, as you shift over to liquids, we don't really think about these, right? The actual cohesion bonds in between to be that strong. Now, they're there. So you do have cohesive forces in a liquid that are there. But they can be much easily broken through. But if they're not broken through, then they're going to act kind of almost like this solid. So now let's keep going with this idea so that we can slowly get back and understand tension. So now, if you think of tension and you think of a rope, so now I'm going to give you another example. So if you have a rope, right, and you suspend this rope, and let's say it is attached on both ends, like so, and now you would put, okay, so on this particular rope, so maybe not a ball because the ball would just kind of roll over, especially, okay, depending on how thick that particular rope might be. But let's say you had a sweater and you hang it over the rope, right? So in the middle, okay, so somewhere, it doesn't have to be in the middle, but let's say if it was in the middle. So you would hang it over. So what you would have is, you would have this and it's going to be hung over, right? So it's going to kind of go over And then from the other side, and let's say maybe it's kind of hanging over like this, okay, and it's being hung on this rope. Now, if you do that ever so slightly, now of course it depends, okay, how this rope is being suspended, but this also is going to have a weight, and it's going to try to pull this down. Now, what's going to happen to that particular rope? So that rope, as you hang this over, so it's not going to be exactly straight anymore. Actually, at the point where you have hung your sweater over. So what's going to happen is, okay, at that particular point, it's going to kind of slightly bend, right? As this is being kind of suspended through. Now, that bend, as you put this object on it, now I'm going to just kind of take the cross section of that object. So, so that object, is kind of sitting there, right, on top. So this is the sweater which is hung over, and I'm just taking the cross section. I'm just kind of removing so just that we can see. Well, what's going to happen is that there's going to be, because of the fact that you have this weight coming down, there's going to be tension now created. And this tension, okay, is going to go kind of in this direction. So it's going to be parallel to that actual rope at those points, right? Now, these two, I'm going to kind of remove this out of the way or move it upwards. So that tension is going to exist, right? So if we were drawing a free body diagram, that would be the case. The same thing would happen if you yourself were hanging out, right? And then you were hanging on, so the tension would be kind of pushed through. Now in this case would be through your arms, so long as you're hanging in and you're statically in equilibrium. Well, in this case, the hands, right, that's the actual rope, that's the extension. And we have tension now being created as you have placed this over. Now, so long as it's being fixed, right, somewhere so that it doesn't just collapse over. And let's say it's in static, right? So it is in an equilibrium. Well, if it's in an equilibrium, it's going to act exactly like we've had right above. So it's going to act like this, like sitting on a table, except it's a different force. It's a tension force. And what's going to happen is that you're going to be dealing with, right, this force of the weight, right, or the W itself, just pulling it down. And then you have the tension itself. So, you'll have the tension on the left, and then you'll have the tension on the right. And if it's in equilibrium, then it's not going to move. So if it's not moving for us, then in the horizontal, right, so in the horizontal components, the tension from the left, so in the X direction in the horizontal, is going to be equal to the tension on the right, okay, on the X, so long as this, sweater is just hanging there and not really moving at all. So these will cancel each other off. So those are going to be gone. However, you are going to have the tension in the Y component there, right? So, you're going to have a tension in the Y component, okay, in both directions, right? So as you're going through. So those particular tensions, so those are going to be your, T, okay, from the left in the Y. So this is going upwards, okay? And then you're also going to have your T, right, on the right going upwards right there. Now, if this is in static equilibrium, if it's not moving, then the addition, because now it's the addition of these two, right, because you have two of them, that should be equal to the force of the weight, right, which is trying to pull it down. So those are going to be equal. So in total, basically, what you would say that you would have this force of the tension is just simply equal to the force of the weight trying to pull it down, right? But it's being kind of tension is being spread over on those two sides. So that isn't anything new if you've talked about forces in the past. And now you can remember, oh yeah, that's right, there's tension, right? So there's some kind of a pull that you have within here. Well, so now I'm kind of stepping you backwards, right? So here you understood the equilibrium. You understood that there were basically particles within that they don't want to get broken apart. So that there's some cohesion there. Well, the same thing happens here in the rope. So in the rope, okay, in those instances where you have hung that sweater or whatever it might be, you're trying not to break those particles either. But this is now acting as a tension force, okay, that you have in there because you're thinking about a rope. Well, now if you come along and you start thinking about liquids, so if you have a liquid, right, so on the surface of the liquid, right, so this is, okay, on the surface of the liquid. If you would do something very similar as we've done with the rope, if you would hang something over. Now, we can't really hang something over the liquid because it's going to have a surface, right? But we can place something on top of the liquid, right? So up above on top, you know, so if you're looking at this from the top, you know, so you would have basically, you know, some kind of, you know, a surface that you would have. And let's say you placed something there. Now, it doesn't matter what it is. So maybe it's some kind of a circular, you know, spherical item, right? It's placed right there. So, you know, we would place it over here, okay, right up above. Now, what's going to happen on that surface, right? So what's going to happen? Well, what's going to happen is that this particular ball, okay, or whatever object that you have, now, if it's too heavy, it's going to break through the surface of the liquid, and it's going to just kind of sink or maybe float. It depends on its density, right? You can think about buoyant forces and Archimedes' principle. Put that up above there. But we're not talking about that. We're talking about you're actually sitting on the surface. Now, so of course it can't be too heavy, and it has to have a certain structure. And it turns out that yes, liquids like solids, the particles, okay, that are holding these things together. So maybe, you know, what I'll do is, so, you know, here's your particles that are at the actual surface. Now I'm going to make them a little bit bigger, right? So obviously they're very tiny, right? But let's say if we had these particles, so they're kind of, you know, lined up, they're rolling over each other, etc., right? Now, what's going to happen is that these particular particles, okay, within the liquid, so this is for liquids, it's not for gases, right? Okay, this is for liquids. They will have cohesion forces. Cohesion forces. You can almost think of them exactly like solids. So these forces, right? So if you would take this, so if I would take all of this, now if I would have all of these, I'm going to just copy it, bring it down here. So unpaste it. I'm going to make them much bigger. So what's happening here is, in between there, okay, there are forces. Maybe let me use, you know, red. So there are forces in between the particles, right? So within here, that are, okay, on each of them, and, you know, they're kind of cohesive. And however, on the surface, so if you take one on the surface, so let's take, you know, one of these, let's maybe this one, what you'll notice is that, you know, that there are these particular forces, okay, kind of all over the place. However, on the surface right here, okay, there is no cohesive force, right, with, you know, the actual, in this case, let's say, imagine that it's the air. So some of them are missing. So here they look like they're kind of balanced out. Okay, and in here, it looks like the interior ones, so the ones over here, are going to be pulling this particular particle more, okay, inwards. So what it's going to try to do is it's going to try to, almost like it's shrinking, right? Like it's trying to collapse it in as much as possible to make it, right? So like as much as possible, these forces, because there's nothing pushing it up, but there's nothing equating them. So it is actually trying to reduce that surface as much as possible, and it's going to bring those things in together. So these cohesive forces exist in nature, in liquids. And these are actually the forces that if you place an object, now sometimes you can think about, you know, either, you know, a water spider, right? You can put a little pin, right? You know, if it's tiny enough, you can place it on. It won't be actually sinking. It's going to be lying there like it's almost a solid, or like the rope with the sweater over it, where it's just sitting there. It's bending that surface, but it hasn't cracked through the actual surface tension. That tension is between those cohesive forces. They're trying to stay together. So they will do exactly like solids. So we can think about, for every action, there is a reaction. as long as they can keep that actual liquid surface together, they will do so. So up on top, if you take a look, so what's going to happen is that you're going to have, you know, let's say something like this, and it's that surface is almost going to bend. And when you put that ball or whatever it is, you know, a spider's leg or something like that, and it's just resting there, then at this particular surface, you're going to have this surface tension, right? And the weakest link is, you know, kind of, as you kind of be looking in here, so the weakest link would be at those exterior parts. So these ones, you know, are kind of supported within these particles, okay, so that you have in there. But within here, okay, as this particular, you know, ball or, you know, a leg or a pin, okay, it's being placed on top, it is trying to break through the surface right here. And if it would break through those particles, so they would shift out and this thing would just fall right in. And it's the surface tension that's going to keep this in. And it works exactly almost like that rope where you have now this tension, right? Which has to be present there because whatever you've placed on top, or if it's the spider, which is just kind of like sitting in the legs, I encourage you can Google that. You can see those pictures. So what you have happening is that, you know, this has a weight, right? So there is a force coming from this weight, which should technically, you think, crash through the liquid and fall down. But because of the cohesive forces that you have, they're trying to stay together like the solid. But the liquid doesn't have those cohesive forces. They're not as strong, but they're there. And they can actually withhold some particular weight depending on the shape and what you have. And what will be happening is that you will have these tension forces as well that are going to be kind of parallel, okay, so within here, so as you're going through here, to the actual, you know, liquid, right? So as you have them, they're on that parallel kind of scheme, you know, right along the surface right there, and you can see that it creates some kind of an angle, right? So you can create that angle. Well, again, just as I've shown you with the rope, where you have the left and the right. Well, in here, we don't really have just the left and the right. This, of course, will depend on how the shape of this is. If it's a ball, okay, if it's that ball, then actually those tensions are all the way around the rim, right? All the way around that rim, that tension is sitting there. Right? So it's like the circumference of that rim, and it's trying to fall through and break all of those little bonds along that circumference. Right? If it's something long and thin, it's going to be on the edges, okay, of there, because it's trying to break through that surface. That's exactly what I'm referring to, you know, right here. You know, it's that surface right at that particular point. So it's those points, okay, of attachment. And this, of course, if it was a ball, this would have been all the way around, okay, sitting there, right? If it's a spider's web and, you know, it's kind of like a circular, okay, a spherical leg that you have, which is pressing against that surface, right? So you can see that the liquid would like wrap around it, right? And you're trying to break through that surface tension. And if it's sitting just there, then what will turn out to be is that, you know, these tensions again, so that's what you have in here. So these are the tensions, okay, that you have. And that particular tension, so I can't really call it left or right because it's all the way around there. So it's that entire tension. So if you would take it all the way around, okay, then you would be able to find out the entire surface tension that has to withhold, okay, against this. And of course, the horizontal ones, again, they will cancel each other off. So, you know, these components, but the Y components going upwards will not cancel this off. They have to, so these components, like in the rope, they have to withhold this if that surface tension doesn't break. So that's just an idea for you, okay, in terms of the intuition behind this. So our force of the surface tension, okay, is going to be equal to the force of the weight if it's holding it up. If this becomes, too much where the surface tension just can't keep it in an equilibrium, it's going to break. And that's what happens for most objects, but some objects will actually stay on the surface. And it turns out that depending on the liquid, so you can measure, just like we measure density, right? So there's different density for water, different density for oil, different density for any other fluids or solids and so on. Well, for liquids, we can find out, okay? And we can do tests to actually check, okay, what that surface tension would be. And we call it a surface tension coefficient. So very often you might see this kind of like a gamma, okay? This is the surface tension coefficient that you have. And this is typically given in force units, okay, per actual, because of the fact that it's on the outer rim, right? Okay, it's on the outer edge that's that surface tension that we want to be able to find out. So this is related to the force per the actual length. So the length or the circumference or whatever length that you have. If it was a pin, right, that was lying down there, then it would be this entire length, okay, that is basically trying to break through the surface. And you would have to know, okay, what is that entire length all the way around? That would be the L. That's the entire thing that it's trying to break through. That's this L that we have. And if you wanted to be able to find out what the full force of the tension is, right? If you know what this length is, if you know what liquid you're talking about, then you can find out this. These are actual in tables. So for water, for oil, and for many other liquids, you can find those out. And then you can certainly find out what this force, okay, of surface tension would be in total. So that is it for this video. My goal was to talk about the surface tension from the viewpoint, okay, of just intuition and trying to understand this. Now, I hope that this is now a little bit clearer for you. So that is it. Thanks for watching. Okay, we'll see you in future videos. Bye, everybody.